VRF, Verifiable Random Function, of TFSC. To safeguard on-chain assets, TFSC also utilizes Verifiable Random Function, VRF, technology. VRF, Verifiable Random Function, was introduced by Silvio Micoli and others in 1999 as a verifiable pseudorandom function. VRF takes an input and generates a random output based on the owner's private key. Additionally, VRF can produce a proof that enables others to verify the correctness of the output using the corresponding public key without knowing the private key. What is a verifiable random function, VRF? A verifiable random function is a cryptographic function that takes a series of inputs, computes them, and produces a pseudorandom output, along with a proof of authenticity that can be verified by anyone. Inputs for a VRF typically include a public/private key pair, also known as a verification key and secret key, and a seed. A public/private key pair is created and a seed is selected. Those values are passed into the VRF, where the private key and seed are used to generate a random number. The VRF then outputs a random number along with a proof. Critically, the generation of a proof makes the function verifiable, while keeping the private key hidden ensures the number is unpredictable. Characteristics of VRF, Verifiable Random Function. Verifiability. The core advantage of VRF lies in its verifiability. The random number generated by VRF can come with a proof, allowing anyone to quickly verify the validity of the proof using the public key, ensuring the authenticity and correctness of the random number. Security. VRF possesses a high level of security, as the generation of random numbers relies on the private key, making it unpredictable and tamper-proof against external attackers. Additionally, VRF implementations typically leverage elliptic curve cryptography, providing robust cryptographic security. Decentralization. VRF can be applied to decentralized scenarios, such as blockchain consensus algorithms. By using VRF to select leaders or validators, it ensures that the entire process does not depend on central authorities, thereby increasing the decentralization of the system. Tamper resistance. The random numbers and their proofs generated by VRF are unique for a given input and private key, making the output of VRF difficult to tamper with. Even the holder of the private key cannot generate different valid random numbers to deceive other participants. Fairness. VRF can ensure that the generated random numbers are fair since they are not influenced by any external factors. This makes VRF suitable for scenarios like lotteries and blockchain consensus, preventing manipulation and cheating. Scalability. VRF exhibits good scalability and can be applied to large-scale distributed systems. Due to the relatively efficient verification process of VRF, it can support a large number of participants in executing random number generation. History of VRF. The concept of verifiable random functions was introduced in a paper published by acclaimed computer scientists and mathematicians Silvio Micoli, Michael Rabin, and Salil Vardhan in 1999. Notably, Silvio Micoli went on to launch the Algorand blockchain, which uses a VRF in its consensus mechanism. There have since been a number of key breakthroughs in the development of VRFs. The technology was improved in 2005 when Evgeny Dodys and Alexander Yampolsky enhanced its efficiency by utilizing a collision-resistant hash function that enabled shorter proofs and keys. Then in 2015, Dennis Hofheinz and Tibor Jaeger created a provably secure VRF using elliptic curve cryptography. And in 2019, Nir Bytansky showed that VRFs can be constructed with general primitives rather than simply algebraic constructions. Many VRF implementations today rely on these innovations. Interestingly, in 2020 researchers proposed a VRF that uses lattice-based cryptography that's secure enough to protect against attacks from a quantum computer, suggesting that VRF can remain an important technology long into the future. VRF use cases. Most RNGs don't produce a random number that can be cryptographically verified, leaving them vulnerable to manipulation and thereby limiting their use cases. By guaranteeing the security of a random number, VRFs unlock a number of important use cases such as Internet security. VRF is used to help secure domain name system (DNS) messages. Zero-knowledge technology. VRF is used in the protocol design for zero-knowledge proofs and zero-knowledge databases. Non-interactive lottery systems. VRF enables provably fair and efficient outcomes for lotteries. Verifiable transaction escrow schemes. VRF can help support automated escrow services that preserve user anonymity. Blockchains and smart contracts. VRF has become an important part of decentralized protocols and applications. VRF in blockchain. A number of Layer 1 blockchains, including Algorand, Cardano, Internet Computer, and Polkadot, use VRF in their consensus mechanisms to randomly select block producers. Elsewhere in the blockchain technology ecosystem, smart contract developers also require a source of randomness for their applications. However, on-chain applications do not have access to a secure RNG due to the deterministic nature of blockchain networks. Using on-chain block hashes as a source of randomness can result in manipulation by blockchain miners/validators who discard blocks with unfavorable hashes and can re-roll the dice, changing the RNG value. Naive off-chain solutions are opaque and provide no proof that the RNG value produced is legitimate, and has not been manipulated by either the data source or Oracle node. Well-designed systems relying on randomness would ideally want it to be provably fair and equally uncertain to all contract participants, and also reduce the risk that an adversary could exploit contracts by predicting its outcomes. VRF, as a cryptographic random number generation method with verifiability, uniqueness, and unpredictability, finds extensive applications in scenarios such as blockchain consensus algorithms, privacy protection, and random draws. As VRF technology continues to evolve and improve, its real-world applications are becoming more diverse, providing reliable randomness and security assurance for various use cases. The integration of these two excellent algorithms by TFSC establishes a solid foundation for the security of TFSC.